Welcome to Debug Log, software engineering war stories, architecture decisions, and lessons learned the hard way. Let's dig in. The promise of event-driven architecture often sounds like a silver bullet. Decoupled services, high scalability, systems that react elegantly to change.
And yet, the title of this piece, The Event-Driven Trap, when your architecture diagram has too many arrows, suggests that perceived elegance can quickly devolve into something far more complicated. What does that too many arrows phrase really signify in practice?
It's the visual shorthand for a system that has become, frankly, unmanageable. It implies a tangled web of implicit dependencies, a Rube Goldberg machine where tracing a single flow becomes a Herculean effort.
So the very flexibility that event-driven design touts can become its undoing, morphing from a clean reactive flow into a sprawling, opaque dependency graph?
Exactly. The initial appeal is clear. Services don't directly call each other. Instead, they publish events, and other services subscribe to those events. This decouples them, allowing them to evolve independently.
Which, on paper, sounds like the dream of microservices realized. It avoids the tightly coupled monolith, allowing teams to move faster. But the article points out a fundamental trade-off that often gets overlooked in the enthusiasm.
It's the difference between syntactic decoupling and semantic coupling. Services might not know who is listening to their events, but they absolutely depend on something listening and reacting appropriately.
That's a crucial distinction. The sender might not care about the receiver's identity, but the overall business process certainly does. If a user-created event isn't processed by the billing service, there's a problem, regardless of how decoupled the services technically are.
It's like sending a letter without an address, hoping the postal service figures it out, but then realizing it absolutely needed to reach a specific person for a critical action to occur. The postal service, the event bus, is decoupled from the sender, but the intent is still tied to a specific outcome.
And the issue compounds because these implicit contracts are often not clearly defined or documented. In a traditional API call, there is a clear request-response contract, often with schema validation. With events, the contract might just be, these fields exist on the event payload.
Which means any change to an event payload, even a seemingly minor one, can have ripple effects across an unknown number of downstream services. It's an invisible tripwire for regressions.
So the architectural diagram starts with a few clean lines, representing clear event flows. But as the system grows, new subscribers are added, new events are introduced, and existing events are modified. Each of those connections is an arrow, and soon the diagram resembles a bowl of spaghetti.
And a bowl of spaghetti where the noodles can change their consistency or flavor profile without telling any of the other noodles. The article highlights how this visual complexity is merely a symptom of a deeper problem, the cognitive load placed on developers.
Understanding a system's behavior becomes incredibly difficult. To comprehend how a single user action, say placing an order, propagates through the system, one must trace a path across potentially dozens of events, services, and queues.
This isn't just an intellectual exercise for architects. It directly impacts debugging. When a bug occurs, how is it pinpointed where the process went awry? Which event failed to fire, which service failed to consume, or which transformation logic introduced an error?
The traditional debugger becomes almost useless in such a distributed, asynchronous environment. The call stack is gone. What's left is a series of independent actions, often with no direct causal link visible at the code level.
Observability tools need to be exceptionally robust to cope. End-to-end tracing, centralized logging, and a way to correlate events across different services and timeframes are necessary. Without that, debugging an event-driven system is like trying to find a needle in a haystack, blindfolded.
And even with sophisticated tools, the sheer volume of events can be overwhelming. A single user interaction might generate dozens of discrete events. Filtering the signal from the noise becomes a significant operational challenge.
The article mentions the challenge of achieving eventual consistency. While it's a powerful concept for distributed systems, it also introduces complexities. What happens if an event is lost, duplicated, or processed out of order?
These are the classic hard problems of distributed computing that event-driven architectures surface rather than solve. Ensuring exactly once processing or maintaining strict ordering across different event streams requires significant engineering effort and specialized infrastructure.
And if not handled carefully, it can lead to data inconsistencies. Imagine a customer's balance being updated in one service, but the corresponding loyalty points not being issued in another because an event was dropped. The system is eventually consistent, but the business impact is immediate and negative.
It's a fundamental tension. The desire for loose coupling and scalability pulls towards asynchronous, event-driven patterns, but the need for data integrity and clear business process execution pulls towards more tightly coordinated transactional approaches. The trap is falling into one without understanding the costs to the other.
The testing strategy for event-driven systems also takes a hit. How is an integration test written that reliably simulates a chain of events across multiple services, especially when order isn't guaranteed or timing is critical?
Unit tests are fine for individual service logic, but for system-level behavior, one is essentially forced into expensive, slow, and often brittle end-to-end tests that attempt to orchestrate a distributed dance.
And the combinatorial explosion of possible event sequences means comprehensive testing is practically impossible. The common paths can be tested, but the edge cases, especially those involving concurrency or failures, are notoriously difficult to reproduce and verify.
Which brings the discussion back to the too many arrows problem. Each arrow represents a potential point of failure, a hidden dependency, a path that needs to be tested, and a piece of context a developer needs to hold in their head.
So what does the article suggest as an alternative or a mitigation? It can't be that event-driven architecture is universally bad, because it clearly has its strengths.
The piece doesn't advocate abandoning EDA entirely. Instead, it emphasizes intentionality and a clearer understanding of its trade-offs. One key takeaway is to scrutinize every event and every subscription. Does this really need to be an event, or is a direct API call more appropriate for this specific interaction?
It's about recognizing when the added complexity of eventual consistency and implicit contracts outweighs the benefits of decoupling. For critical, synchronous business processes, a direct transactional API call might be the simpler, more robust choice.
Another recommendation involves explicit event contracts. Treating event schemas with the same rigor as API contracts, using schema registries, and versioning events carefully can mitigate some of the hidden dependency issues.
This is about making those arrows visible, labeling them, and understanding their purpose. It's like moving from a spaghetti diagram to a subway map, still complex, but with clear lines, stations, and destinations.
Precisely. The article also touches on the importance of domain boundaries. Events should ideally represent meaningful state changes within a specific bounded context, rather than generic data dumps that can be interpreted in countless ways by various subscribers.
Because if an event is too generic, it effectively forces every subscriber to understand the full context of that event, violating the very principle of separation of concerns it was supposed to enable. It turns into a broadcast channel where everyone has to listen to everything, just in case.
And that leads to services becoming overly chatty, subscribing to events they don't strictly need just to be safe. That's another source of too many arrows, not just for explicit dependencies, but for latent ones too.
The final point that emerges is about managing state. Event-driven systems often encourage each service to maintain its own local state. But when that state needs to be consistent across multiple services, the coordination becomes a significant challenge.
Techniques like event sourcing, where the system state is derived from a sequence of events, can help, but they introduce their own set of complexities related to data storage, querying, and snapshotting. The answer is rarely simple.
So the core message seems to be, event-driven architecture is powerful, but it's not a default choice. It's a tool with specific applications, and its use requires a deep understanding of its hidden costs, particularly in terms of operational complexity and cognitive load.
The trap isn't the architecture itself, but the uncritical adoption of it. The diagram with too many arrows is a visual alarm bell, signaling that the system has outgrown its initial design principles and is becoming a maintenance nightmare.
It forces the question, when does the flexibility of decoupling become a burden of implicit coupling?
And how much complexity is one truly willing to embrace for the promise of scalability?
That's a wrap on this debug log. Join us next time for more engineering war stories and hard-won lessons. If any of this hit close to home, subscribe and tell your team.
Ship it carefully.